Hello and welcome to Selection with Sathi. The Master Theorem is the most powerful tool for solving divide and conquer recurrences. If you are preparing for GATE CSE, placements, or coding interviews, this is the one theorem you absolutely must master. Today we will cover the complete extended form of the Master Theorem, all three cases with intuition for why each one works. A quick decision shortcut that handles 95% of exam questions, and 4 fully worked examples including a GATE previous year question. Let us begin. The Master Theorem applies to recurrences of the form T of n equals a times T of n over b plus theta of n to the k times log to the p of n. Look at the parameters on screen. A is the number of subproblems, it must be at least 1. B is the factor by which the input shrinks, at each step, it must be strictly greater than 1. N to the k times log to the p of n is the work done outside the recursive calls. This includes both the divide step and the combine step. The key idea is to compare a with b to the power k. This comparison tells us whether the recursion does more work, or the non-recursive part does more work, or they are balanced. That gives us 3 cases. Let us look at each one. Case 1 applies when a is greater than b to the power k. In this case, T of n equals theta of n to the power log base b of a. Think of the recursion tree. Each level creates a times more subproblems, but each subproblem is only b times smaller. Since a is greater than b to the k, the work increases as you go deeper. The leaves of the tree do the most work. The tree is bottom heavy. For example, T of n equals 8 T of n over 2 plus n squared. Here a is 8, b is 2, k is 2. b to the k is 4. Since 8 is greater than 4, this is case 1. The answer is theta of n to the log base 2 of 8, which is theta of n cubed. Another quick example, T of n equals 9 T of n over 3 plus n. A is 9, b is 3, k is 1. 9 is greater than 3. Case 1 gives theta of n squared. Case 2 applies when a equals b to the power k. This is the balanced case. Every level of the recursion tree does roughly the same amount of work. The answer depends on the log exponent p. When p is greater than -1. Which is the most common situation? T of n equals theta of n to the k times log to the power p plus 1 of n. For the usual case where p is 0, this simplifies to theta of n to the k times log n. The classic example is merge sort. T of n equals to T of n over 2 plus n. A is 2, b is 2, k is 1, p is 0. b to the k is 2, which equals a. So T of n equals theta of n log n. There are 2 rare subcases for completeness. When p equals -1, T of n is theta of n to the k times log n. When p is less than -1, T of n is just theta of n to the k. Case 3 applies when a is less than b to the power k. Here the non-recursive work dominates. The root of the recursion tree does the most work. The work decreases at each level, so the total is dominated by the first term. T of n equals theta of n to the k times log to the p of n. When p is 0, this is simply theta of n to the k. Example, T of n equals to T of n over 2 plus n squared. A is 2, b is 2, k is 2. b to the k is 4. Since 2 is less than 4, this is case 3. The answer is theta of n squared. Another example, T of n equals T of n over 2 plus n. I is 1, B is 2, K is 1. B to the K is 2. 1 is less than 2. Case 3. The answer is theta of n. Here is the quick decision method that you should memorize for exams. Given any recurrence T of n equals a T of n over B plus theta of n to the K. Step 1. Identify A, B, and K. If there is a log factor, note P. Usually P is 0. Step 2. Compute log base B of A. Step 3. Compare log base B of A with K. If log base B of A is greater than K, it is case 1. Answer is theta of n to the log BA. If log base B of A equals K, it is case 2. Answer is theta of n to the K times log n. If log base B of A is less than K, it is case 3. Answer is theta of n to the K. This 3-line shortcut covers 95% of GATE Master Theorem questions. You only need the extended form with P when the recurrence has an explicit log factor.
Let us work through our first example. T of n equals 4T of n over 2 plus n. Step 1. Identify the parameters. I is 4, B is 2, K is 1, P is 0. Step 2. Compute log base B of A. Log base 2 of 4 is 2. Step 3. Compare. Log base 2 of 4 is 2 and K is 1. 2 is greater than 1. So this is case 1. The recursion dominates. The answer is theta of n to the power log base 2 of 4, which is theta of n squared. Intuitively, 4 subproblems of size n over 2 create so much recursive work that the linear combine cost is negligible. Example 2. The merge sort recurrence. T of n equals to T of n over 2 plus n. A is 2, B is 2, K is 1. Log base 2 of 2 is 1, which equals K. This is case 2. Since P is 0, the answer is theta of n to the 1 times log to the power 0 plus 1 of n, which simplifies to theta of n log n. This makes perfect sense if you think about the recursion tree. There are log n levels, and at each level the total merge work across all nodes is O of n, and work per level times log n levels gives n log n. Merge sort is the most important application of case 2. Example 3 involves the log factor. T of n equals 3T of n over 4 plus n log n. Here A is 3, B is 4, K is 1, and P is 1 because of the log n factor. Log base 4 of 3 is approximately 0.79. Comparing, 0.79 is less than K, which is 1. So this is case 3. In case 3, the non-recursive work dominates. The answer is theta of n to the K times log to the P of n, which is theta of n times log n. Notice how the P value of 1 carries through into the final answer. This is why the extended form matters. Without tracking P, you would incorrectly get just theta of n. Our final example is a GATE previous year question. T of n equals 16T of n over 4 plus n squared. Step 1. A is 16, B is 4, K is 2, P is 0. Step 2. Log base 4 of 16. Since 4 squared is 16, log base 4 of 16 is 2. Step 3. Compare. Log base 4 of 16 is 2, and K is 2. They are equal. Case 2. The answer is theta of n squared times log n. Many students rush and pick theta of n squared, but case 2 adds the extra log n factor. The recursion tree has log base 4 of n levels, and each level does n squared total work. So the total is n squared times log n. Remember, when log base b of a equals k, always multiply by log n.
Let me share 4 important tips for exams. Tip 1. Memorize the simplified 3-line shortcut. Compare log base b of a with k, greater means case 1, equal means case 2, less means case 3. This handles 95% of questions. Tip 2. Case 2 with p not equal to 0 is rare, but it does appear in gate. Remember the 3 subcases based on whether p is greater than, equal to, or less than -1. Tip 3. The Master Theorem does not apply to recurrences like t of n equals t of n minus 1 plus n, that is subtract and conquer, not divide and conquer. For subtract and conquer, use substitution or the recursion tree method instead. Tip 4. Always check that a is at least 1 and b is strictly greater than 1 before applying the Master Theorem. That was the complete Master Theorem for divide and conquer recurrences. We covered the extended form with all 3 cases, the quick decision shortcut for gate, and 4 worked examples including a gate previous year question. Practice applying this to different recurrences, and you will never get stuck on these problems. For more concept videos like this, check out Selection with Sathi. Like, subscribe, and keep learning. See you in the next one.